we will now consider the curl of a vector field. So the curl of the differentiable vector field f, which is given by p, q, and r as those component functions of, say, x, y, and z, is the vector field del cross f. So here I'm going to take the cross product of two vectors. The first is the del operator. So it's d dx, d dy, and d dz. And then the second is the vector field p, q, r. So if I want to take that cross product, okay, I should get dr dy minus dq dz times I plus, actually I'm going to write this as minus using that cross product. So it's going to be dr dx minus dp dz times j, and then plus dq dx minus dp dy times k. And so that gives the curl of our vector field. So what is the significance of this curl, which itself is going to be a vector field? Well, let's look again in two dimensions and think about our vector fields as representing the velocity of a fluid. So in this case, we have the vector field p, q, and say 0 for the z direction. And they're only functions now of x and y. So the curl is actually going to represent a measure of how much rotation around a point we see at that point. So how much rotation we see in this fluid. So what you can imagine is that I could take like a little stick and I could put it in the fluid like this. And then you see that we have smaller vectors pushing here on this end and then larger vectors pushing here on this end. And so what we expect to happen is that this stick will tend to rotate. We will have it start to rotate in this direction here because we have a larger vector pushing on it, and then rotate a very tiny amount in this direction. And so this particular vector field has non-zero curl because we can see that the fluid is rotating by putting some sort of like definite object like a stick or something in there. We'll see that it's going to get rotated. In this case, it's being rotated counterclockwise, so we would probably say that it has positive curl, assuming that we've defined, say using like our right hand rule, that the counterclockwise direction is going to be positive. Now we could look at another vector field, say this one, and then maybe we can put another stick in this vector field. Okay. And notice as I draw that stick, right, that all the vectors that are kind of pushing against it are the same length. And so this vector, this stick is not going to rotate at all in this vector field, okay, because all the vectors are in the same length. So pushing at it from any point along the stick you're not going to get any sort of rotation. And so here, this vector field has 0 curl. Okay, so these are two nice examples of vector fields that have a positive curl and a non-zero curl. I will mention, because they're not written here, that in this case we saw these two vector fields before. This one was y and then minus x. That's the one that had no divergence, but in fact has a positive curl. And then this one that had 0 curl here, that was the vector field negative x, negative y. And we see that's the one that had negative divergence in our previous video. Okay, so let's write down our interpretation here of curl. So we're going to say, let F be the velocity of a fluid. Then the fluid near XYZ will tend to rotate about the axis in the direction of the curl. So the curl of the vector field is itself a vector, and that vector is going to point in the direction of the axis around which our fluid is going to rotate. In the case of our non-zero curl, you can think about taking your fingers and curling them with your right hand, taking your fingers and curling them in the direction of this rotation, and you get your thumb pointing up when you rotate them, when you curl your fingers, and that will represent the fact that the curl vector in this case is only going to be in the positive z direction. It's only going to have a positive k hat component. Okay, so the vector itself that you get from the curl, that's going to be the axis around which you see the fluid rotating.